A few weeks ago, NASA did something they'd never done before. They collected material from an asteroid and brought it back to Earth. Or at least, we think they did.
Yeah, the reason we can't say for sure is because we're recording this episode on September 21st. The team working on this mission to study the asteroid called Bennu is expecting the capsule holding those samples to land outside of Salt Lake City, Utah on the morning of September 24th, which for you has already happened. So I guess you all know more about how this sample return went than we do.
Welcome to Tiny Matters. I'm Deboki Chakravarti, and I'm joined by my co-host, Sam Jones. And if you think about it, Sam, by recording this today, before the sample drops, we're kind of communicating with the future.
Yeah, definitely, Deboki. That's definitely what we're doing.
Okay, fine. Maybe we're not. But we are going to be spending today's episode of Tiny Matters traveling around in time and space to learn more about how we collect samples from places beyond Earth. How do we get those samples, and how do we bring them back to our planet? And what are the challenges that we face when those samples arrive?
The mission to collect material from the asteroid Bennu is called OSIRIS-REx.
So OSIRIS-REx is one big acronym, and if you're ready for it, it's Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. So it's very long, but it essentially summarizes all of the objectives of the mission.
That's Sierra Gonzalez, who is on the Mission Operations Engineering team at Lockheed Martin. It takes a lot of people to make these missions happen, and Lockheed Martin is part of a larger group that includes NASA and the University of Arizona.
The team that Sierra works on is specifically involved with the day-to-day operations that keep the spacecraft safe and running so that the science teams can learn from the asteroid. We asked Sierra what those teams are looking for in the samples.
Inevitably, it all comes back to that acronym that makes up the OSIRIS-REx mission. And the O in OSIRIS-REx means origins. So we believe that there may be ingredients to life in this sample, since the type of asteroid that our sample is coming from is a carbonaceous asteroid. So we're hoping to find some organic molecules, maybe water or minerals, and this will help us answer some questions of perhaps how did Earth get the water and organic molecules that allowed life to evolve here? And one theory is that asteroids similar to Bennu delivered the necessary ingredients to an early Earth. Besides the O, there's resource identification. So there's been lots of talk in the news about asteroid mining. So this sample could also tell us what potential resources are available on asteroids like Bennu.
OSIRIS-REx launched on September 8, 2016, arrived at Bennu at the end of 2018, and then began its journey back to Earth in 2021. And as we mentioned, this is NASA's first time bringing back samples from an asteroid. But this isn't the first mission of its kind. In 2010, the Japanese Aerospace Exploration Agency spacecraft Hayabusa was able to return to Earth with a small bit of sample from the Itokawa asteroid. And in 2020, they collected even more samples from Hayabusa 2, which had traveled to an asteroid called Ryugu.
To collect samples on Bennu, OSIRIS-REx fired nitrogen gas at the surface of the asteroid to disrupt the pebbles and dust and rock, floating them into the sample collector head that Lockheed Martin calls TAGSAM, or Touch and Go Sample Acquisition Mechanism. There are so many acronyms.
The TAGSAM head was then stored in a capsule, and that capsule is what returned to Earth as OSIRIS-REx flew by and on to its next mission, which we'll talk more about later.
You might be wondering why we need to go to space to get these samples. Sure, we want to know more about the possible organic molecules in asteroids, but why do we need to go to the asteroids when scientists can study them when they land on our planet in the form of meteorites? The reason is contamination. When meteorites land on Earth, they become much harder to study because microbes and other materials from our planet get mixed up in those samples and make it hard for us to distinguish what came from space versus what came from Earth.
So, having the ability to collect samples from asteroids and other things in space and then bring them back to Earth so we can study them without contamination is an incredible opportunity for scientists. In the past, spacecrafts have returned with samples collected from a comet and solar wind, which is the stream of particles being released by the sun's corona. But possibly the most famous sample retrieval mission is from Apollo 11 in 1969. Obviously, Apollo 11 is best known as the first time a human ever stepped foot on the moon. But the Apollo missions weren't just about who we sent to the moon. They were also about what we could bring back. And that was both exciting and terrifying.
If you've been listening to Tiny Matters for a while, you might remember that in an episode we posted back in June, Deboki did a tiny show and tell about an article she'd read regarding the lunar samples that came back with Apollo 11. So for today's episode, we decided to talk to historian Dagmar de Groot, whose research was the basis for that article. Dagmar is an associate professor of environmental history at Georgetown University.
So just to start out, if we're back in that decade, can you give us a sense for what the questions people would have been thinking about in terms of microbes and contamination as they're planning this mission?
So first question, is there life on the moon? And by 1961, there had been centuries of speculation about whether life actually existed there. Some people in the 19th century, even the late 19th century, still believed that the moon was inhabited by intelligent beings. Even the early 20th century, prominent astronomers thought there might be swarms of bugs on the moon that accounted for changes in the appearance of craters. And by 1961, really very little was known about the lunar surface. There were still serious ideas about plankton that might have drifted onto the moon from interstellar space, or at least lichens in the cracks on the moon's surface. There's also a question then about how life might have originated in the first place and whether it could have begun elsewhere. And by 1961, early investigations into that topic seemed to suggest that life could originate anywhere where there was chemistry similar to that of the early Earth.
Dagmar told us that around that time, the early 1960s, astronomers were also beginning to understand just how extreme climates on other planets are, like the cold on Mars or unbelievable heat of Venus, which reaches temperatures hot enough to melt lead. And while that's not particularly habitable to us, it didn't seem impossible for something like a hardy bacterial spore to be able to survive those conditions.
That led Carl Sagan and other planetary scientists to wonder what could happen if an organism capable of surviving, say, the lunar surface, were to make it back to our planet. And looking through history, they saw plenty of reasons to be worried. In the US, for example, colonialism brought not just new people, but also their diseases. The spread of smallpox led to deadly epidemics within indigenous communities that hadn't been exposed to the smallpox virus before. We have an episode about bioterrorism where we talk more about how Europeans weaponized smallpox against Native people, using it as one of the tools in the many acts of violence they wielded against indigenous populations as they took their lands and enslaved them. We've linked to it in the episode description if you want to learn more.
Carl Sagan and others then leaned on that sort of history to argue that, if you get microorganisms into a population that has no experience of them, it could be absolutely catastrophic. And then a much more difficult question to answer was, could microorganisms from other worlds actually thrive on Earth? So if you take them out of that environment and bring them to our relatively lush environment from our perspective, could they then multiply? And really the assumption of people like Sagan was that life was barely eking out an existence on the moon, if it existed. And you bring it to Earth and it's going to just explode.
These are all questions that you might spend a while thinking about and forming safety plans around. But this was the 60s, and the US was in a space race against the Soviet Union. President John F. Kennedy had declared his ambition to send an American to the moon by the end of the decade, which meant there wasn't a lot of time. The question was, could we quickly send someone to the moon while also minimizing the risk of hypothetical moon microbes making it back to Earth?
And the answer that was emerging by 1961 and really clarified at a big government conference in 1964 was no, that would not be possible. It could not be prevented. And that is the answer that was never communicated to the public, or for that matter, to policymakers.
That being said, there was a lot of work put into creating a quarantine protocol designed to protect the planet. The central piece of this plan was the Lunar Receiving Laboratory, also called the LRL. This was a facility in Houston meant to house the samples that came from the moon, and its primary concern was preventing contamination.
But as Dagomar pointed out to us, contamination is a two-way street. On the one side, you have the possibility that our planet will be contaminated by the hypothetical moon microbes. And on the other side, you have the possibility that our planet will contaminate the samples we've worked so hard to get. Think about the meteorites we talked about earlier, which land on our planet and end up contaminated with our own earthly materials, making it impossible for us to cleanly piece together their history. So designing a quarantine protocol for these lunar samples involved two very important goals: prevent the things outside from getting in and prevent the things inside from getting out. The problem was that it's really hard to design a facility that can do both. And inevitably, the people building the Lunar Receiving Laboratory had to prioritize one goal over the other.
And a good example of that would be air pressure, right? If your air pressure is high, everything inside of your facility is going to try and push out. And if your air pressure is low, of course, then everything outside the facility is going to tend to get in. And even just this question of air pressure was really challenging because you had scientists, geologists, who wanted to study any rocks, anything brought back from the moon. And it was imperative for them that those samples not be contaminated by terrestrial microbes. But then you had the biologists, bioscientists. Of course, they were in charge of managing quarantine, and their main goal was to keep anything inside, right? Keep any microbes that might be in the lunar samples from blowing out. And ultimately, they won, so that air pressure was low inside of the Lunar Receiving Laboratory. But it's just an example of the kind of tension that immediately surrounded the construction of the facility.
Alongside these design challenges, the LRL was built so quickly and with so many decisions in flux that the end result was a facility that just did not work the way it should. For example, the autoclaves, which are meant to sterilize equipment, kept failing, even as the astronauts were landing back on Earth. And looking at these issues within the LRL and the other protocols put into place, Dagomar argues that if there had been microbes on the moon that came back with the astronauts, they probably would have made it out of the facility into our environment.
The astronauts, when they got to the LRL, were placed in quarantine for 3 weeks. But had there been a health emergency that any of the astronauts faced, and had it been bad enough, they could have been removed from quarantine and taken to a hospital. Which is ironic, right? Because one of the things that plausibly could have caused a health emergency in the first place would have been a dangerous lunar microorganism, right? So that as soon as it was almost proven to be dangerous, the astronaut would have been removed from quarantine.
So the bad news is that we would probably not have prevented a moon microbial crisis. The good news is that whatever we brought back from the moon was safe. There wasn't a crisis to prevent. Still, Dagomar's work is particularly important for highlighting the lack of communication about these risks at the time, and the challenges we face when thinking about risk, which is relevant in a number of fields, including climate change and AI.
And Dagomar told us that for sample returns that don't involve humans, like the OSIRIS-REx mission, some of those questions around quarantine will be a lot more straightforward to handle. But of course, that does not mean that bringing back samples will be easy, and the engineers and scientists involved still have to worry about the Bennu samples getting contaminated.
When we started building the vehicle here at Lockheed Martin Space, we've been considering how to store and work with this material from space. We want to prevent contamination as much as possible, but also give insight into what this has been exposed to.
Sierra told us that one of the ways scientists will be able to track contamination of the OSIRIS-REx samples are witness plates, which are made of either aluminum or sapphire. The job of these plates is essentially to collect the different materials and contaminants that parts of the spacecraft have been exposed to, assembling a record of possible contamination that scientists can factor into how they analyze the samples. On top of contamination, there's another potential issue that engineers had to design around: heat.
When the return capsule comes in through re-entry of the Earth's atmosphere at more than 27,000 miles per hour, it will see temperatures upwards of 5,000 degrees Fahrenheit, which is very hot. So that return capsule will insulate it so it remains at a stable temp. We want to make sure it's nice and protected and limit the exposure to oxygen and water.
As we mentioned at the start of the episode, the return is scheduled for September 24th. And as you can imagine, there are a lot of things that can potentially go wrong, like a hard landing that causes the capsule to open up.
So like musicians, we don't go to a concert without practicing and practicing with all the pieces together, from spaceflight through landing in the Utah desert up to curation of the sample in Houston. So we've done several rehearsals to practice all kinds of scenarios for that preparation. If we're looking at both good, easy days and very challenging days. So the ground team has done some work too, including a drop test in Utah, where we dropped a engineering unit by parachute from a helicopter.
It's really cool to hear about all of the engineering that goes into planning these missions, but it's also fascinating to hear about all of the unexpected bits of science that turn up along the way.
Bennu has been throwing a lot of surprises at us from the very beginning. We originally thought Bennu was going to be a sandy asteroid based on the imagery we got here on Earth. And then when we arrived, it was boulders on top of boulders, on top of rocks, on top of boulders. So we had to change a lot of our engineering mindset of how we were going to collect this sample. And then when we were orbiting the asteroid, we actually saw activity on the surface. In fact, it was almost like it was spitting pebbles at us. And then, of course, when we collected our sample, we collected so much, an overabundance of sample, that we were overflowing and needed to speed up the time frame to stow the sample and move up everything by a week to get it stowed and safely captured so that we didn't lose any more precious sample. So there's lots of surprises along the way that, surprised all of us. And it keeps it interesting because in space, you can't design for everything. It's millions of miles away. You can't go up and fix anything either. So there's lots of really cool problem solving that gets to happen along the way.
Once the capsule holding the sample lands, a team will bring it to a temporary clean room in Utah and then prepare for its journey to the Johnson Space Center in Houston, where it'll be kept in a permanent clean room. The sample that's coming back is expected to be around 250 grams, and most of that will be saved. But the rest is going to be sent around the world to be studied at various institutions, including the Japanese Aerospace Exploration Agency, or JAXA.
JAXA shared some of their asteroid samples with NASA, a process that included some very earthly challenges. The biggest one was the pandemic, which kept scientists who were involved in the sample exchange from being able to travel. Finally, in 2021, delegates from Japan were able to bring the samples over, but they were carrying the precious cargo in heavy carry-on bags, which meant they had to coordinate with TSA and the airlines to make sure their samples wouldn't have to go through the X-ray.
I was stressed enough bringing my cat through security. I cannot imagine having to worry about precious space samples.
I know. And on top of that, it was November, so, Thanksgiving time, which is just the absolute worst time to be traveling. But fortunately, the samples made it.
And I love that story because it's like there are all these brilliant people working together to operate a spacecraft on an asteroid, but even exciting scientific discoveries eventually have to face things like the TSA. Lockheed Martin is going to be transporting the OSIRIS-REx samples from Utah to Houston in a military C-130 plane, so luckily there shouldn't be any TSA issues.
So in this episode, we've gone to all sorts of weird places. An asteroid, the moon, the 1960s. But now we're going to look to the future. And when we were talking to Dagmar about his work studying the environmental history of space, he mentioned that we seem to be in the early stages of another space age.
So a few things happening right now that are really profoundly transformative. And I don't know how many people at this point realize that they're happening, but I think that will change in 5 to 10 years. One of them is that the big bottleneck in getting to space is getting wider and wider. That bottleneck is the price of actually lifting something into space. Renewable rockets, and SpaceX is really taking the lead with this, are reducing the cost of sending stuff into space by orders of magnitude. And it can't be overemphasized how groundbreaking that truly is.
And talking to Sierra, it was just so cool to learn about what it's like to be a part of one of these projects, where you're putting years of work into operating a science experiment that's not even on this planet with you. So I asked Sierra how it feels to be waiting for the sample that OSIRIS-REx gathered to return to Earth.
Oh, this is such an incredible opportunity to be part of this wonderful team full of intelligent people. I started on the program in 2018, just before we arrived at the asteroid, and I was a systems engineer at the time. And it was just an eye-opening experience of what's possible. And coming back as a fall protection engineer and in another role as a flight operations engineer, and getting to see the sample come home after being on the team who retrieved the sample and stowed the sample for its safe return. It's a bittersweet feeling too, that it's coming back and it's almost ending its primary mission, but it's also very exciting the type of science we're going to get back on Earth and the other science that we're getting by extending the life of the spacecraft.
That bit at the end that Sierra is alluding to is the future of OSIRIS-REx. Because if everything goes smoothly on September 24th, which you all know more about than we do right now, that doesn't mean OSIRIS-REx is over. Shortly after the sample capsule is released by the spacecraft over Utah, the team will fire up the spacecraft's engines so that it can fly off to another asteroid named Apophis on a mission called OSIRIS-APEX. OSIRIS-APEX is not the new dinosaur hybrid from Jurassic World. And it also won't be able to collect any samples, but it will still be able to use the instruments and cameras on board to tell us more about the asteroid and give ideas for future missions to space. Tiny show and tell time. Let's do it.
I can go.
Cool.
Okay, so for today, for my tiny show and tell, I want to talk about something near and dear to my heart, sleep. But sleep...
I slept horribly over the last few nights, so this is really hitting home right now.
Then this science is for you. It turns out that you have a lot in common with the oysters in this lab experiment who are being subjected to artificial light throughout the night. So the scientists wanted to learn more about how oysters might be responding to light pollution and whether or not that is affecting their circadian rhythm. And so they kept some oysters in a tank that basically had artificial light on at the night. And even when they had a really low level of nighttime light, like less than the amount of light you'd get from a full moon, they found that the oysters, their circadian rhythm got thrown off. And that's really interesting because oysters don't have eyes, but they do have some kind of specialized cell that we don't know about that does respond to light. So basically to study the way that the nighttime light was affecting oysters and their circadian rhythm, the researchers looked at the movement of their shells because that is like the main behavioral response, I guess, that we can study when it comes to oysters because they open their shells to feed, to breathe, to mate. So they use electrodes to actually track when the shells are opening. And so they compared these oysters in this artificial light tank to oysters that were in a control tank that could actually get dark at night. And they found that the exposure to artificial light at night led those oysters to keeping their shells open at really odd times. Like there was actually like a lot more shell opening activity in the early evening, whereas normally they would be more of like kind of middle of the day shell opening sort of thing. They also looked at specific genes that are known to turn on at specific times of day, like kind of daytime specific genes versus nighttime specific genes. And they found that the artificial light oysters, basically those genes were like on all the time. Like there wasn't really as much specificity to the time of day. The researchers do note in this article that I was reading that we don't know the long-term consequences of this still. Like we don't know a mechanism to say that this can lead to health issues. And oysters are important to environments and to economies even. So this is something obviously that could be important in the long run, oyster insomnia.
Yeah, that's so interesting. Me and oysters.
Yeah.
Me and oysters. I wonder what the equivalent of an eye mask for us is for oysters. I guess it's just like, they don't know what exactly is responding, right? So
yeah, they just know that there must be some kind of photoreceptive cell. So once you can put an eye mask on that cell,
I know.
they're good. They're golden.
All right, that's my new startup. Eye mask for oysters. That's kind of cool. I like that. That's cute. Thanks, Boki. The story that I want to talk about today is about how researchers have sequenced the RNA from the Tasmanian tiger, which was this wolf-like marsupial. It technically went extinct in 1936, but that was the last animal and it was living in a zoo at that point. And so why do I think that this is cool? Why is this interesting? Well, we hear a lot about researchers being able to sequence DNA from sometimes millions of years ago. The problem is that DNA it tells you things, but it still does not tell you a lot. A lot of times I think you see things like your genes are 97% the same as a banana. You're not that special. And it's like, true, this is why comparative genetics is a thing. I think overlap between humans and chimps is something like 98 or 99 point something percent. So yes, DNA, it's important. It tells you what genes are there, but it doesn't tell you what genes are actually expressed. And by that, I mean which ones are actually taken from that DNA blueprint and transcribed into RNA, which then, RNAs do their own thing in your cells, but a lot of them also are then turned into proteins, which have a ton of different functional roles. Without that happening, you would not be here. So the reason that it's really cool to be able to actually sequence RNA from extinct species is because you have a much better understanding of the genes that were actually transcribed, like the genes that they had that actually had more of an impact on what they were like as animals. So the Tasmanian tiger that scientists got RNA from has been dead since the late 1800s. And it was actually in the Natural History Museum in Stockholm. And it was just because some researchers came across this very dried out looking Tasmanian tiger. And they wanted to see if they could sequence the RNA. And they did, which is really, really cool.
Yeah, that's really cool. Did they talk about how they were able to get a hold of that RNA? Because like you said, it's very fragile. It's really hard to get.
So I guess what they did was they actually collected 6 samples from skin and muscle of this desiccated Tasmanian tiger. They brought it to the lab and then they did their best to use a pretty standard extraction technique to get as many isolated nucleotides as possible. And then what they did was they ended up actually using a computer algorithm to compare those RNA sequences with a database that had the genomes, so the DNA of different animals, plants, fungi, bacteria, viruses, as well as the genome, the DNA, from the Tasmanian tiger. And so from that, they were able to figure out that about 70% of the RNA sequences that they were looking at were reliably from the Tasmanian tiger and not just other. Speaking of contamination earlier in the episode, very easy to get some contamination in there. So there was some contamination from, of human RNA in that sample because this specimen, this desiccated specimen, had been sitting around for something like 130 years. People were picking it up, touching it, moving it, putting in different spots. So yeah. But it's just kind of cool because they're able to still glean a lot more information than you'd be able to with just a DNA sample alone.
Yeah, that's really cool.
I just was like, I feel like a good opportunity to talk about how the fact that we have a lot of overlapping DNA with things like bananas, we're expressing those genes quite differently most of the time.
Yeah.
So, yeah, it's good. It's overlap. This is evolution, right? We are all connected. All of us, animals, plants, everything. We are all connected in one way or another.
Yeah.
But the way that our genes are expressed has changed so much over time, and it makes us who we are and it makes us different. And so being able to figure out how the Tasmanian tiger was actually different from other species that it coexisted with that maybe still exist today, I think that's just kind of cool. It just tells you so much more. DNA is cool, but I think I did my PhD in RNA, so I'm like, RNA is cooler.
Yeah, that's awesome. Thank you. Thanks for tuning in to this week's episode of Tiny Matters, a production of the American Chemical Society. This week's script was written by me, and it was edited by Sam, who is also our executive producer, as well as by Michael David. It was fact-checked by Michelle Boucher. The Tiny Matters theme and episode sound design are by Michael Simonelli and the Charts and Leisure team. Our artwork was created by Derek Bressler.
Thanks so much to Dagomar de Groot and Sierra Gonzalez for joining us. If you have thoughts, questions, ideas about future Tiny Matters episodes, please send us an email at tinymatters@acs.org. And if you are still listening and you have not rated and reviewed us, please do that. It's super duper helpful. We would appreciate it. Also, another way to support us is by picking up a Tiny Matters coffee mug. So we've left a link to those in the episode description. You can find me on social at SamJScience.
And you can find me at Okidoki Boki. See you next time.